Okay guys, I tried to record that Zoom review session earlier, but it turns out the video is a little too long for me to upload to YouTube, and the video of me working the problems was not very visible in the final product. So I'm just going to do a short video recap right here and talk about some of the things that we went over in the review session in case you weren't able to join in and you had some of these questions. If you have further questions beyond what I would cover in this video, please do just send me an email and I will get back to you as you are studying Hardy-Weinberg today. Alright, so where we started out was with this chapter 11 video. It's called 19 on the sheet. It comes from a different textbook, so don't worry about that number. This was a worksheet that I posted Sunday evening, and it reviews everything from chapter 11 to include Hardy-Weinberg. There is an answer key at the end of the sheet, so as you work through it, you can certainly check your work. So this worksheet is handy, gives you a little bit of review of what the Hardy-Weinberg equations actually are, some of the conditions that are necessary. It talks about the idea of gene flow and genetic drift, which are important for you to understand for this Hardy-Weinberg quiz as well. So we started out with question 1 here, and you can see that we worked it all out together. These are the answers that we came up with. So if you haven't done it yet, maybe pause the video, try to work it for yourself, and then come back and check your work. So in question 1, we're looking at albinism. Albinism is a recessive phenotype, meaning if you are albino, you have to have the genotype of homozygous recessive. So if we use A's, that would be not albino, right? And the lowercase a would be albino. And albino just means no pigmentation is produced. So if we're talking about a person, they would have very, very pale skin, very light blonde hair, blue eyes. It's present in animals as well. They would be white with the red eyes. You may have seen albino rabbits before. That's what we're looking at here. So if we look at question 1, we have determined in this population 4% are albino. Now, how do we write 4% as a decimal? It's 0.04. We're going to need to work with decimals whenever we're working with Hardy-Weinberg. If you keep it as just the whole number 4, as in 4%, you're going to get the wrong numbers when you start to square and square root, so please make sure you're using the decimals. So when it says an investigator determines that 4% of a population is albino, that means 0.04 is going to be our proportion of homozygous recessive. Because in order to have the albino phenotype, you have to have that genotype, right? There's no other genotype you can have and still be albino. We know from our Hardy-Weinberg equation that the frequency of homozygous recessive genotypes in a population is Q squared. So Q squared is given to us right from the beginning of the question. 0.04 is Q squared. Q squared, again, what that actually represents is the percentage or frequency, if we write it as a decimal, of the population that is homozygous recessive. Well, once we know Q squared, we can use some simple math to figure out Q. If we have Q squared and we take its square root, we get Q. So if we have 0.04 and take its square root, we get 0.2. So it's a simple matter of taking the square root of both sides of your equation. This is not 0.02. Be careful with your math here. 0.2 times 0.2 gives you 0.04. So make sure that you don't have an extra 0 in your answer. You can always put this in a calculator to double check if you need to. Well, now we know Q, and it's easy to go from there to P because of this portion of Hardy-Weinberg right here. P is the recessive, or is the frequency of the dominant allele. Q is the recessive allele. They must add up to 1. We only have 2 alleles possible, one dominant, one recessive. So if you take both of their frequencies and add them together, it should add up to 100% of the alleles in the gene pool. So that means our Q of 0.2, if we subtract it from 1, we're left with P. And that gives us 0.8 is our value for P. At this point in time, we have now unlocked all of the keys to solving any calculation we need to with Hardy-Weinberg. We know P, we know Q. So when we think of this equation, P squared plus 2PQ plus Q squared, we know all of the P's and Q's, and we can plug them in as needed to figure out the rest of our frequencies. So as we move on, in question E, now that we know P squared, easy, we square it. 0.8 times 0.8 gives us 0.64. And again, what is that? That is the frequency of our population that is homozygous dominant. Homozygous dominant would be 2 dominant alleles, or capital A, capital A. We can go on to G and find the value of 2PQ. 0.32. If we multiply 2 times 0.8 times 0.2, we get this, 0.32. And what we have calculated now is the frequency of the population that is heterozygous. Heterozygous, if we write it as the genotype, again, one dominant and one recessive allele. So capital A, lowercase a. And so finally in question I, what percentage of the population has normal pigmentation? There are two ways we can figure that out. Probably the easiest way, go back and look at our initial question. 4% of the population is albino. So what percent of the population is normal? Well, 100% minus 4 gives us 96%. So it's as easy as that. Now, can you also figure it out from these earlier calculations? Well, absolutely. Normal pigmentation is going to be genotype capital A, which was, if we go back and look, 64%. Also, the genotype capital A lowercase a, or the heterozygous genotype, would also give you normal pigmentation. So here we know that that would be 32%. If we add that together, we get the same answer, thankfully, of 96%. So there's two ways you can figure out that question. So from there we moved on to question 2. Now, if you are watching this video and have not yet done question 2, now would be a good time to pause it and try to do the question on your own, and then come back and listen to the explanation. Okay, question 2. 49% of our population cannot taste PTC, and it tells us a dominant allele is necessary to taste the substance. So if you can't taste it, that means you have to be homozygous recessive. Our dominant allele is for tasting PTC. Our recessive allele, you can't taste it. So the question tells us 0.49 is the frequency of the recessive phenotype. Now, to have a recessive phenotype, we know that your genotype has to be homozygous recessive, or 2 lowercase alleles. In our equation, that corresponds to Q squared. So our question, 49% cannot taste it, is telling us right off the bat what is the value of Q squared. So that would be 0.49. To find Q, we take the square root of 0.49. Again, be careful with that. It's 0.7, not 0.07. P is easy to figure out because we know P and Q add up to equal 1. So these two here must add up to 1. And that's always how we figure out P or Q. If we know one, we can figure out the other. So that gives us a P of 0.3. We square it to get p squared, that's 0.09. So how would I interpret this? 0.09 would mean the frequency of homozygous dominant individuals, or 9% of this population would have a genotype that is 2 dominant alleles for the tasting of PTC. And finally, our last term, 2PQ, that's our frequency of heterozygotes. If the question were to ask us what percent of the population has a heterozygous genotype, we would multiply 2 times P, which is 0.3, times Q, which is 0.7, and we would get a total of 0.42, which is 42% of our population. Okay, so from here, we started to talk about some other aspects of Hardy-Weinberg, like the genetic drift, bottleneck effect, founder effect, and how does that impact Hardy-Weinberg calculations. So I'm going to switch over to the other worksheet. This is the worksheet called More Hardy-Weinberg Practice Problems. You got this in class. It was the half sheet of paper. There is an answer key on Edmodo. You'll have to scroll down to the day when I posted it. I believe that was March 11th, our early release day, and there is an answer key attached to that post, so you can use that to check your work. We just did one example here. That was question number 4. And this is very similar to the questions that you're going to see on your quiz. So let's take a look at what we did here. In 4, it's telling us that there's a population of 5,000 individuals. We have round seeds, which is dominant. We have long seeds, which is recessive. So if we use letters, that's going to be our round seed allele. And this is going to be long. That's lowercase r. Okay? We have 4,050 plants that have long seeds in the population. We just said that long is recessive. So if 4,050 plants have long seeds, that means 4,050 out of our 5,000 total are going to be homozygous recessive. Right? That is the genotype that you have to have in order to have long seeds. So 4,050 divided by 5,000 gives us 0.81. Since this is a genotype here, we know that both alleles, because they're recessive, this would be the Q squared genotype. So Q squared equals 0.81. The question doesn't ask us for this value, but we have to start here in order to figure it out. We take the square root, we get a Q of 0.9, subtract from 1 to get a P of 0.1. Okay, in B, it asks how many plants are heterozygous. We already know 2PQ is going to give us our frequency of heterozygotes. So that is 0.18. Anytime it says how many, you take your frequency, you multiply it by your total population size, which here is 5,000, and the number you get, 900, that's your answer. 900 plants would be heterozygous. Okay, moving on to C. Now we have a new situation happening. We have birds stopping to eat some grass seeds. They poop it out later, start a new colony of grass that only has 500 individuals. 375 with round, 125 with long seeds. Remember, long is our recessive, so we're going to start there, right? Always start with recessive. 125 out of 500 gives us 0.25. That's our recessive genotype, or Q squared, is 0.25. That gives us P of 0.5, Q of 0.5. What is the term for this scenario? This is the founder effect. Founder effect is when you have a small subset of a population being transported to a new place, and then they start a brand new population from scratch. So in our last question here, is this in equilibrium? That's a simple no. We know it's not in equilibrium because look at our allele frequencies. They have changed. Anytime you have allele frequencies change from one population to the next, It is not in Hardy-Weinberg equilibrium, which means the population is evolving. I hope that was helpful.